Thank you for coming to this second day of Buffet-4 workshop. Today we have another exciting program of model comparison updates, and we'll start with a very tasty one, risotto, presented by Amber Young. So Amber, whenever you're ready, just share your screen and yeah, the floor is yours.
Okay.
Yeah, we can see your
There
screen.
we go. Okay, great. Trying to hide the meeting controls and everything too. So does it look good on your end? Hopefully, yes.
Yeah, all good.
Okay, perfect. So, hi everyone. Thank you so much for having me here today. My name is Amber Young, and I'll be presenting the sort of one of the newest dishes on the menu for cuisines called risotto. And also thank you so much to all of my collaborators and sous chefs who've been helping me with getting everything started, including Eleonora Alay, Michael Himes, and Geronimo Villanueva. So to start, risotto essentially stands for Retrieval Intercomparative Simulations of Trailblazing Exoplanet Observations. And so when honing in on what risotto means and what we're doing, just think about the R in risotto and how we're focused on retrieval models, essentially. Um, but first, to start, I'll go over just very top level, sort of the basics of retrieval modeling. So the idea and the sort of top level goal for retrieval models is to be able to use it as a tool to extract information about a given planetary spectrum, in this case, particularly of interest for like exoplanet observations. And so you can imagine if you had a data set of an exoplanet, which is indicated on the right here by the black error bar data points. In this case, it's a simulated spectrum of modern Earth. Let's say you had a model that you wanted to, that was able to produce a spectrum, and you wanted to be able to fit that model to the data. Essentially, the retrieval analysis process flows like an iterative process to be able to fit different suites of models to a given or a particular data set. So you can imagine starting with sort of like an initial guess for what the atmospheric state would be for whatever you're seeing within the data spectrum. And you'd use a given forward model, in most cases, a radiative transfer forward model that simulates all the physics behind the overall reflectivity of the planet to be able to generate a spectrum. And so then the next step would then be to use something like an instrument simulator to be able to degrade the forward model spectrum to the same observational quality as the observed or simulated data set. And then using statistical analyses like the likelihood evaluation and fit metrics to be able to statistically determine the goodness of fit between the model that you've generated and the data set that you're comparing to. And so you can imagine, for example, a fit metric being the reduced chi-squared. And if you had a reduced chi-squared that wasn't anywhere near 1, that would indicate a poor fit to the data. And so you'd go through the loop and adjust the parameters to be able to get a new atmospheric state, a new spectrum, and continue the cycle. And do that until you've achieved a statistically good fit between the model and the data set for reduced chi-squared, that be around 1. And so just to illustrate this and how the retrieval process can work in real time, again, let's assume that we have a simulated data set here, which is indicated by the gray points. And you can see in real time how our model spectra is trying to fit for different features that correspond to the data set. In this case, we're trying to fit for water vapor feature at around 0.95 microns. And then you can also fit for planetary parameters like pressure using the Rayleigh scattering slope that's indicated here in the spectrum. And so at the end of the day, what a retrieval analysis produces for you is, for one, if you're achieving a statistically good fit in the data, then you can understand the collection of models that were able to best reproduce the data set. And that is essentially articulated or illustrated through marginal posterior distributions, where for any given retrieval parameter, that range in distribution space essentially represents the range of possible values for that parameter that's able to model or reproduce that particular data set. So in this case, again, since we were fitting for features like the water vapor feature, then we have an uncertainty or a range of values of water vapor abundances that correspond to what could produce that particular feature. And then similarly for the pressure, values of pressure that are able to reproduce that Rayleigh scattering slope. And so a good indication or a good analysis for the posterior distributions is you want to see a particularly peaked distribution that's near some sort of known or truth value, whatever. If it's a simulated data set, you want to get back what you put in, so something that's similar to truth, and that is peaked near truth. And then also looking at the range of uncertainty on the given posterior distributions. If it's a really tight, well-constrained posterior distribution, then you have relatively good knowledge of that particular parameter. And that's what you'd want to shoot for in an ideal case or an ideal situation. And so just to start off, I'll go over a couple of different statistical techniques or inference methods for retrievals. The first being Markov chain Monte Carlo analysis, which everything that you saw in the previous slides and those simulated retrievals were done using this process. So you could see how iteratively the retrieval is exploring parameter space. And again, the idea is to map out the regions of parameter space that are able to reproduce the data and fitting for each retrieval parameter by looking at the resultant posterior distributions that are produced through the analysis. Nested sampling is another popular inference technique. It's very similar to MCMC, but with the added benefits of being able to estimate the evidence as well for a particular model. And finally, optimal estimation, which is a slightly different technique, but it provides it combines the prior information with the observational data set in order to determine the single best fit solution for a given data set. And so you can kind of split up retrievals into three main processes. So the first being the forward model. Again, if we're talking about radiative transfer, this is the underlying physics that goes into recreating or producing a spectrum. So you can do that directly with the forward model, or you could use something like a grid-based approach where those radiative transfer calculations are done pre-calculated and done ahead of time. So the retrieval model analysis is just a matter of interpolating between grid points to be able to analyze and explore the parameter space. Then you can also, sort of look at AI and machine learning techniques as well as sort of an alternative for forward modeling approaches. And then the second portion to a retrieval model is typically some sort of instrument noise model. Again, it can be used to either simulate the data set in and of itself that you're then going to retrieve on. That's often the case for things like mission development, understanding observational capability of a particular mission. If you want to predict how well an observatory will do, you want to simulate the data set and then retrieve on that. But of course, you can use actual observational data as well and then retrieve on that directly. And then step 3, in implementing either any of those statistical analysis techniques to be able to map out and determine the posterior distributions for given retrieval parameters. And so Malbec has been sort of carrying and putting forward the charge toward understanding the forward model aspects and comparing, codes that have particularly different radiative transfer schemes or different line lists that they're pulling from, and just exploring that portion of the model analysis for retrievals. And in terms of the simulated noise and the data sets that we're working with Risotto, we are assuming a simplified noise model, and we're working with simulated data spectra all throughout this case to be able to really hone in on the differences between retrieval analysis techniques and whether or not they agree or disagree for different types of planetary scenarios. So the premise behind Risotto is essentially these key themes. The first being to first order, just model benchmarking. So being able to have folks participate by running their retrieval models for a given planetary case and then understanding how well they agree or disagree for different planetary cases, and going through and identifying what are the sources of discrepancy between different retrieval models as they run with sort of to default. And ultimately, hopefully, honing and fostering connections within the retrieval community so that we can better establish standards and common practices for exoplanet retrievals, and really preparing ourselves for the influx of continuing data that's coming in from JWST, where retrieval analyses are often used to interpret those data sets, and forthcoming missions like the Habitable Worlds Observatory, where again, we want to be able to look at the mission capabilities and understand what observations we need to make and how well the observations need to be in order to gather the information that we want for a particular set of targets. And so just to dig into this a little bit more in terms of those three themes, in terms of the benchmarking, like I alluded to, essentially we want folks to be able to come into this with a low barrier to entry, in the sense that you have a retrieval model, maybe you've been using it actively, and we just want you to be able to run a suite of atmospheric cases without any model adaptation for your code. Do it in the way that you think is best and see what the output comes out to be and where everything lies in terms of what your model produces sort of by default and defaulted analysis. And then in terms of evaluating sources of discrepancy, in particular, we're looking for things where maybe the posterior distributions are not very tightly overlapping with each other. Maybe there's potential bias in the distributions, where if we know what the true value is for a given parameter and those distributions are offset from what the true value is, understanding why there's offsets is one thing that we want to look into. Potential degeneracies, so correlations between different parameters and how they might be influencing one another across parameter space. And then also evaluating model limitations. Are there different retrieval models that work well for certain planetary cases versus others? Are there specific retrieval analysis, statistical analysis techniques that are better suited for particular questions versus others? These are the kind of questions and things that we want to address while evaluating sort of potential differences that might arise between the retrieval model outputs. And then essentially what we want to do in terms of the comparative analysis is we do want to look at sort of a wide suite of generalized planetary cases from that spans, terrestrial planets all the way up to gas giants, in terms of being able to retrieve on those different spectra, and also having a wide range of wavelength space, and incorporating different types of observations from direct imaging to transit spectroscopy, just to name a couple of examples. And so I'll go over the current progress for Risotto so far. If you're already a part of the Cuisines mailing list, then you'll know earlier in the year I put out a welcome letter that was kind of introducing the start of Risotto, trying to gather participation, garner interest into the group, and through that email communication and broadly spreading the word, for Risotto in and of itself. Now we have an established email list that is comprised of about 25 people so far, which is great. I think we've gotten really great momentum and initial interest in the retrieval modeling and intercomparisons in general. And so now's a great time to sort of get involved and become associated with the group. And if so, in terms of what we've done so far for meetings, we have held a few meetings, 5 meetings so far, and we typically meet once a month. And I'll share more information about the meetings on the last slide if you're interested in participating and getting involved. But so far, what we've done is we've kind of initialized what we want to do for the initial retrieval tests. And particularly, we're focusing on GJ1214B, which is a continuation of the Malbec protocol study. So it's a great place to start. Malbec has done such great work in kind of fielding and helping with gathering a place for us to start and be able to carry on that work. So just to kind of summarize where we're at in terms of incorporating the Malbec studies into the retrieval analyses. So from the Malbec protocol paper, which was published earlier in the year, there's a number of forward model intercomparisons here that have generated spectra for this particular transit study case for GJ1214B, which is a mini Neptune. And essentially what we've done is we've taken the average of these different forward models and kind of generated a simulated data set with randomized Gaussian noise. And we're just having the community to first order reproduce a forward model that's similar to the T3B case study and see whether or not your forward model is already within the range of these different forward model cases from Malbec, and then go forward to do the study. And so if you are somebody who has already participated in the Malbec intermodel comparison, then you already have a spectrum to start with. That would be the backbone of being able to do the retrieval analysis. So again, huge emphasis to jump on the bandwagon now and definitely get involved if you're already involved with Malbec. But so I was kind of alluding to this in the previous slide, sort of the workflow. Again, we want folks to have a sort of low barrier to entry to be able to do the retrieval models. We have an initial case study prepared where you can test what your forward model produces and then compare that to the forward models that have already been included in the Malbec study. And then at your liberty, retrieve on that particular spectrum, which again, we just took the average of the Malbec spectra and we added noise to it. And that's essentially what your forward model is trying to compare to and reproduce. And we're asking the community to sort of run this with your own model defaults. Don't make any adaptations to the retrieval analysis. Use your best judgment and approach to the retrieval. We give hints in terms of what retrieval parameters to include based on the spectral features that are indicative of that particular planetary case. But outside of that, we want you to run things to default and see what comes out of it. And then phase 3, which we want to work toward, is being able to complete additional case studies, sort of expand the parameter space and kind of look into other planetary scenarios, which we can test our retrieval models. But that's sort of down the road, and we're still working toward that. And so next steps or immediate next steps. So a lot of folks have already done the forward model comparison with their model and the Malbec study, just to kind of give a sanity check for where the forward models lie in terms of being within that range of the Malbec data set. A lot of people have done that already, and some have done the initial sort of retrievals on this particular planetary case, and we're already seeing differences that correspond to like, how are you treating background background gases? And do you have additional priors that relate to those background gases versus not? We're already starting to see differences there in terms of how people are going about the retrieval process. And we want to dig into that more so in the coming months as we continue to analyze things. But then, of course, we do want to develop and standardize the outputs for comparison, because right now folks are just running their retrievals. They're making plots on their own. They're posting their corner plots, their posterior distributions, and we're kind of by eye doing those types of comparisons. But we do want to sort of standardize a framework for the outputs, which is why we're really lucky to have Arthur Adams as part of the Risotto group. And we're really excited to hear about those synergies between the JWST proposal that he put in and how that sort of overlaps and synergizes really well for next steps for Risotto. So we're excited about those opportunities there to collaborate. And then next step will be to sort of finalize the cases that we would want to include in the protocol paper, and just continuing to think up those case studies and case comparisons. And in terms of continuing to draft the paper, essentially we do have the overleaf template for the protocol paper, so that's initiated, and we're starting to gather folks together to incorporate descriptions of their models as an easy, again, low barrier entry to be able to participate as you can and as you're willing to. And so if you're interested in joining, please feel free to follow the link to the Google Docs spreadsheet where you can add your contact information. And then that is what I use to be able to see who's involved in the mailing list, and you'll get the emails based on providing your corresponding information in the spreadsheet. And if you are already a part of the Cuisines Slack, feel free to join the specific channel that's dedicated to risotto, and you'll be able to get meeting notifications, updates, reminders, summaries of the meetings after each one, that type of stuff. You'll all get that information through being a part of the email list and being a part of the Slack channel as well. And if you want to come to our next meeting will be held remotely. They're all always remote. And it'll be Thursday, November 21st at 11 a.m. EST. So if you have any questions or want to learn more, please feel free to reach out to me via email. And with that, I will take any questions.
Thank you, Amber. Does anyone have any questions? Yeah, great work. Feel free to put your questions in the chat. I can read them out loud, or just unmute and ask your question. While people are thinking, I have a question. Oh, Duncan, go ahead.
I was just wondering that we know that from like the transiting exoplanet ERS, there was a lot of retrieval work done there. I don't know if you had any sort of, I guess my question is, I was wondering if you had any sort of discussions with them about their work in trying to understand tables.
That's a good point. I think in trying to gather participation from various different retrieval models, we did have some contacts who were part of that team. And so we have a little bit of participation there. Joe Barstow, who was involved with that intercomparison, just to think of a name off the top of my head, she's included in Risotto already. So we're kind of trying to stay plugged into that for sure. Yeah.
All right, Thomas.
Hey, Amber, that was really an awesome talk. Thank you. I was wondering, among the variety of inference models like, Monte Carlo, optimal estimation, nested sampling, what is the distribution roughly that we have in Risotto in terms of code? Is it like mostly nested sampling or the other?
Right. So right now we do have pretty good participation that spans those two fronts. Yeah, traditional MCMC analysis and nested sampling. And I know in particular, like Geronimo has some experience with optimal estimation. And so he is planning on sort of contributing on that front. So yeah.
Okay. Thank you. Is it open to machine learning type of retrieval, like a, I don't know, neural network, something like that as well? Or?
We're definitely open to it, although at the moment, I don't believe we have explicit, like active participation with a model that incorporates machine learning algorithms. So if you have contacts in that area or you want me to reach out to somebody in particular with that type of model,
I have
definitely
some.
open to it. Yeah, cool.
Thank you.
And of course, I should say Michael Himes too has
Sure.
expertise in that area, but I don't want to overcommit him too much because he's contributing in other ways. So.
All right. I actually have a small question. Well, maybe not very small, but have you thought? I mean, you kind of started talking about this yesterday, but have you thought about sort of specific scientific questions you wanted to answer with this intercomparison, or maybe more specifically, what would be the main source of model discrepancy that you anticipate?
So it is going to be sort of a tiered approach to evaluating model discrepancy. And I think that that is definitely the heart of what we're trying to understand and research is kind of like, what are the sources of discrepancy and are there differences between actual retrieval analysis techniques? Because we've seen with previous intercomparison studies like the Barstow et al. Comparison, where they pretty much adapted analogous radiative transfer forward models and still got discrepant results across the board for the three models that they were intercomparing. So we want to be able to explore that a little bit more, but then also kind of expand the parameter space to different planetary cases, because that will show sort of the growing pains or the discrepancies between formalisms for retrieving on gas giants versus retrieving on terrestrial planets, or if there's differences in terms of wavelength space that correspond to kind of those discrepancies as well. So building on that is what to do.
Yeah, awesome. Well, looking forward to it. Thanks, Amber. We're just at a half hour, so the